Okay, so the next quiz is only on implicit differentiation, so all you have to worry about for the next quiz is just this one unit, and I wouldn't even consider this as a relatively difficult unit. I think it's relatively simple. It's just a little abstract in its meaning, but it's really not too bad. The best way to practice it is definitely with practice problems, and you just kind of get the hang of it. So what implicit differentiation is just you kind of have one free variable that you take derivatives with respect to. So velocity, right? This is the example I always like to go back to. Velocity, what are the units of velocity? Meters per second, right? And meters per second is position with respect to time, right? Where meters is your measurement of position and seconds is your measurement of time. So, and velocity is the derivative of position. So, all you're really doing with the derivative is finding the rate at which one thing changes with respect to how another thing changes. So, in the case of velocity, you're measuring how position changes with respect to time. And you're doing this with all derivatives. Generally, right, we normally see derivatives in the form of some kind of x thing. So if we're given y equals 3x squared, and we take the derivative of that, and we get dy dx equals 6x, all this is really saying is that the derivative of y with respect to x is 6x. So the rate at which y changes with respect to x is 6x. It's a very similar thing to velocity, just a little bit more abstract because it's not, position and time and stuff like that. So all you really need to know is that anytime you take the derivative of a term with a variable in it that is not x or t or whatever your general variable is, you have to do that variable, so in this case it's dy, with respect to d, your regular variable, in this case x. And most of the time it will be y and x and stuff like that. Generally speaking, that's how these problems are written. The only time it really gets more complicated than this is in a unit called related rates, which is the most difficult unit in this class, or if you take Calc 3. But both of those things are in the future, and for some of you, a lot of you probably aren't taking Calc 3 anyway, so this we can kind of leave it as this. So if we took the derivative of 2y cubed, y acts the same as x for the purposes of derivatives, right? It's like literally just a regular variable where it's a power rule, right? That 3 comes down in front, multiplies with that 2 to give you 6y, and then you drop the power by 1, so 3 minus 1 is 2. 6y squared. But then since we took the derivative of a non-x term, we have to do dy dx because we just took the derivative of y with respect to x. And then over here, we just took the derivative of x. Technically, every time we took the derivative of something with x in it, we should be writing dx dx, which means the derivative of x with respect to x. But just as you'd simplify 3 divided by 3 to 1, you would also simplify dx divided by dx to 1. So you just kind of multiply it by 1 and we just don't write it. But yeah, all you really need to know is every time you take the derivative of like y or not x, you got to write dy dx. Okay, and then generally speaking, you'll be asked to solve for dy dx. That means you're actually finding the derivative. So like in the case of this, solving for dy dx is the same as solving for any other variable. You just do algebra to it until you isolate this and get it by itself. So in this case, right, we just want to divide both sides by 6y squared, which simplifies to dy dx equals 2x divided by y squared. And then the first practice problem here, you just go through term by term and take the derivative like you would any other derivative problem. Derivative of x squared is 2x, right? We know that. And then the derivative of y cubed is going to be 3y squared, normal power rule. And then since we just took the derivative of a non-x term, we got to write dy dx equals, and then the derivative of 4, that's a constant, so it's just 0, right? So then now, just like the last problem, we want to solve for dy dx, right? We want to get it isolated. So the first thing we do is we subtract 2x from both sides. So that becomes 3y squared times dy dx equals negative 2x. And then now we want to get dy dx by itself, so we just divide by 3y squared. So dy dx equals negative 2x divided by 3y squared. We could add in another wrinkle of 2 different y terms, but it would just kind of be exactly the same. So we go to take the derivative of this, the derivative of 2y cubed. That y comes down, or that 3 comes down, I should say, multiplies with that 2 to give us 6. Y, and then we drop the power by 1. So 3 minus 1 is 2. Derivative of 4x squared, 4x squared, that 2 comes down. 8x, normal power rule. Derivative of y is just dy dx, right? Because it would be 1, just like the derivative of x is 1. But then we took the derivative of a non-x term, so it would be 1 times dy dx, which we can just write as dy dx. And then the derivative of x to the 6th power is just 6x to the 5th power, right? Basic power rule problem. Oh, and sorry, I forgot to write dy dx here because we took the derivative of a non-x term. So we've got 6y squared dy dx plus 8x minus dy dx equals 6x to the 5th. So, and again, our goal is to solve for dy dx. We've got 2 dy dx terms here, and we need to isolate that, get it on one side. So the way we do that is we subtract 8x from both sides, 6y squared dy dx minus dy dx equals 6x to the 5th minus 8x. And what that does is it gets us all of our dy dx terms on one side of the equal sign. And that's good because now we can factor out a dy dx from these two terms. So this is now dy dx all times 6y squared minus 1 because we factored out a dy dx. And then that equals 6x to the 5th minus 8x. So then now we can divide both sides by 6y squared minus 1. And now we are just left with dy dx equals 6x to the 5th minus 8x, all divided by 6y squared minus 1. So group your terms, get all your dy dx terms on one side of the equal sign, get all of your non-dy dx terms to the other side of the equal sign, factor out that dy dx, and then divide by everything else. Okay, and now just to see how implicit differentiation would work within the context of a product rule problem. So our term on the left is a product rule, right? With our first term being 3y to the 4th, and then our second term being e to the x. So we come over here. U is our first term, so 3y to the 4th. V is our blue term, so that would be e to the x. The derivative of u is going to be 12y cubed times dy dx, right? Because we just took the derivative of a term with a variable other than x, and then the derivative of e to the x is just e to the x, right? So now we go across. So this becomes 3y to the 4th times e to the x plus 12y cubed dy dx times e to the x. So that's the derivative of the left-hand side of our equal sign. And then the derivative of the right-hand side, derivative of x squared, that's just 2x. So now remember, our goal is to isolate the term that has dy dx in it and then factor it out. So we do that by subtracting 3y to the 4th power times e to the x from both sides. So we get 12y cubed dy dx times e to the x equals 2x minus 3y to the 4th power times e to the x. So then now we just factor dy dx out from this term. So that's 12y cubed times e to the x and then now we divide by that 12y cubed e to the x, and we are left with dy dx equals 2x minus 3y to the 4th power times e to the x divided by 12y cubed e to the x. And this would be our final answer. So it can be a lot of writing, but the process is very consistent, pretty much the same from problem to problem. The only wrinkle is that, when you're doing a product rule or a quotient rule, you only take the dy dx when you take the derivative of the y term within the context of the rule. All right, so this is a similar problem, just with a little bit more intensity. So we do a product rule here. Derivative of y to the 7th is 7y to the 6th times dy dx. And then the derivative of 4x squared is just going to be 8x. So then this whole thing is going to be 8x times y to the 7th plus 4x squared times 7y to the 6th times dy dx. And we could simplify that 4 and that 7 to be 28. And then minus 2, because derivative of 2x is just 2. Derivative of x to the 5th is 5x to the 4th. And then the derivative of 4 times y cubed is just going to be 12y squared. So remember, our goal is to get all of the dy dx terms over to one side. So we're going to move everything that's not dy dx away. So that would be, so we would subtract negative 8x y to the 7th. So we would end up with 28x to the x to the 2 times y to the 6th dy dx equals 5x to the 4th plus 12y squared plus 2 minus 8x y to the 7th. And then we would factor out a dy dx from this side. We get 28x squared y to the 6th. And then this would equal, right, just this same thing, because we haven't done anything to this side yet. So, but then we would divide both sides by 28x squared y to the 6th, and we would be left with our final answer, which is dy dx equals this whole thing divided by 28x squared y to the 6th. This would be our final answer. And then as for implicit differentiation with the quotient rule, it's pretty much the same as it is with the product rule. So if we have our numerator as our u, that will be 2x, derivative of 2x is just 2. And then we have our denominator as y cubed, derivative of that is just 3y squared dy dx, right? Because we took the derivative of a term without x as our variable, so it has to be with respect to x. So then we just plug that into the formula of u prime times v minus u times v prime, all divided by v squared. So that will just be 2 times y cubed minus 2x times 3y squared times dy dx. And this will all be divided by y cubed, and that will be squared. So this will, and then this all equals the derivative of x squared, which is just 2x. So we can simplify this, clean it up a little bit. 2y cubed minus, and then this 2 and this 3 multiplied to give us 6 times y squared times x times dy dx, all divided by now y to the 6th power equals 2x. So then we can multiply both sides by y to the 6th power to get rid of that denominator, right? And give us 2x y to the 6th. So then now we want to get all of our dy dx terms to one side and all of the non-dy dx terms to the other side. So we'll subtract this 2y cubed from both sides. So we'll get negative 6y squared times x times dy dx equals 2xy to the 6th minus 2y cubed. And then now we factor out that dy dx from that term, and we're just left with negative 6y squared x equals, and then just this stuff again. And then finally, we divide both sides by that negative 6y squared x, and then we are left with, right, dy dx equals 2x y to the 6th minus 2y cubed divided by negative 6y squared x. And you would generally just leave it like this. So that's how it works with the quotient rule. Pretty much the same. Sometimes it gets a little sloppier, but it's really the same line of thinking as the product. Okay, and then the last rule that we really have to worry about is the chain rule. So it's really just the same as the product and the quotient rule. So this is a chain rule problem, right? And I guess so is this. So if we have sine, right? So sine is our outside function. So this is a chain rule problem where our outside is f of x, and that is equal to sine of x. And then our inside function is y. So the derivative of f of x is, right, just cosine x. And then the derivative of g of x is dy dx, right? So then now we need to plug this into the form f prime of g of x times g prime of x, right? Our chain rule formula. And then, so then this ends up being cosine of y times dy dx. And then that's, all right, so that's for that term. So then now let's continue to our e to the y term. So this one will be blue. So this is also a chain rule problem where our outside function is e to the x. Our inside function is just y, right? Our derivative of e to the x is just e to the x. And then the derivative of y is just dy dx, right? So we need to plug it into the same formula. And so that'll be e to the y, right? Because that's f prime of g of x times dy dx, because g prime of x is dy dx. So our derivative, at least of the right side or of the left side, is cosine y times dy dx plus e to the y dy dx, and then the whole thing equals 2, because that's the derivative of 2x, and then the derivative of 3 is just 0 because it's constant. So that's what we're left with. And then, as you remember, we just want to get dy dx, all the terms with dy dx to one side, and then all the terms without dy dx to the other side. It's already done for us, right? Both of our terms that have dy dx in them are already on the left side. The only one that doesn't is already on the right side, so that's perfect. So we can just go ahead and we can factor it out. So we're left with cosine of y plus e to the y, and then the whole thing equals 2. So then we just divide by cosine y plus e to the y, and we're left with dy dx equals 2 divided by cosine y plus e to the y, and that would be our answer there. And you could be asked these kinds of questions with respect to a tangent line equation. So this is how that would shake out. So basically with any other tangent line equation, the first thing you want to do is take the derivative, right? And that's no different here. So what we can do is we can rewrite, this is our function. So we can rewrite x, or the cube root of x squared as x to the 2/3 power. We can rewrite the cube root of y, right? We can rewrite this as y to the 2/3 power. And we can just keep that as 4. So then we go to take the derivative of that, right? Y to the derivative of x to the 2/3 is 2/3 times x, and then we drop the power by 1. 2/3 minus 1 is a negative 1/3, and then plus, same thing for the y term, right? 2/3 y to the negative 1/3, but then dy dx, right? Because every time we take the derivative of a variable that's not x, we have to throw in a dy dx, or whatever that variable is. And then the derivative of 4 is just 0, because it's a constant. So then now, we could also move these to the denominator, so 2 divided by 3x, or 3x to the 1/3, which could be cube root of x, if you'd like to simplify it this far. Same thing with y, then times dy dx equals 0. So then now we want to get all of our terms with dy dx over to one side and all of the ones without it to the other. So we will move this 2 divided by 3 times the cube root of x over to this side. And we will get 2 divided by 3 cube root y equals negative 2, 3 times the cube root of x. And then, this is times dy dx. So then we just factor out the dy dx, and then we divide both sides by 2, divided by 3, cube root of y. And then when we do that, we're left with dy dx equals negative 2 divided by 3 cube root of x divided by 2 divided by 3 cube root of y. So we can flip this. Dy dx equals negative 2 divided by 3 root 3x times 3 root 3 y divided by 2. And so, right, this 2 and this 2 cancel out, this 3 and this 3 cancel out. So we're just left with a negative third root of y divided by third root of x. So this would be our answer here. And then we would go to plug that into our tangent line, right, because we're looking for the equation of a tangent line. Same as before, y minus y1 equals m times x minus x1. It gave us our x and our y value, right? This is our x, so negative 3 root 3. So this become a plus 3 root 3 because you got that double negative. And then our y, it actually tells us, is 1, right? So instead of y1, we would write 1. And then now, this is our m, so this is our derivative. So we want to plug in this where x equals 3 root 3 and y equals 1. So I would probably just write this as negative 1 because the third root of 1 is just 1. And then I would probably leave this alone. Just leave it like this. Plug this in where you see m. Make some room for it first. Something like this is how you would answer this question. Yeah, you get the idea. This would be your answer. And then just combining together a chain rule and a product rule. So this first term here would be a chain rule. So we would get our outside function, it would be tangent of x. Our inside function would be x minus y. Derivative of tangent is secant squared. And then the derivative of x minus y would be 1 minus dy dx. And then we would plug this into the chain rule formula, right? F prime of g of x times g prime of x. So then that would be secant squared of x minus y times 1 minus dy dx. And then this would all equal, this is going to be a product rule where 2x is our first term and then y cubed is our second term. So u equals 2x, derivative of that is just 2. And then our v equals y cubed, derivative of that is just 3y squared dy dx. And then this, so then we would go across here to get 2y cubed plus 6y squared x dy dx. And then minus 1, derivative of 1 is just 0. So then we want to, remember, we want to get all of the dy dx terms on one side. Before that, though, we have to expand this out. So we want to distribute this secant squared to both of these terms. So we get secant squared times, or secant squared of x minus y times 1. So we'll just leave it like that. And then minus dy dx times secant squared of x minus y. And then that equals just, we're leaving the right side of the equation alone for the time being. And then that would not be a minus. So then this is what we're looking at. So then now we want to get all the dy dx terms over to one side and then all of the other ones to the other side. So I'll choose to add dy dx to both sides here, or this term to both sides. So this cancels out. And then I will also choose to move this 2y cubed over to the other side. So this becomes secant squared of x minus y minus 2y cubed equals 6y squared x dy dx plus dy dx times secant squared of x minus y. So now, basically just however you can get all of your terms with dy dx over to one side, get all of your other terms to the other side, and then here we can just factor out a dy dx from this side, 6y squared x plus secant squared of x minus y, and then same thing here, right? And then we can divide both sides by that 6y, just the inside of the parentheses on the right, or brackets, I guess. So then we are left with secant squared x minus y minus 2y cubed divided by 6y squared x plus secant squared of x minus y equals dy dx. That would be our final answer for this problem.